A single torpedo detonates beneath a warship. Within seconds, the entire vessel lifts out of the water as a massive gas bubble forms underneath. The keel bends, the hull buckles, then gravity takes over, and the ship breaks in half before sinking to the ocean floor. This is the terrifying reality of modern naval warfare. But there's one class of warship that refuses to go down easily. Aircraft carriers weighing over 100,000 tons face these same underwater threats while simultaneously battling 60-foot waves in the open ocean. So how do these floating cities survive what would destroy almost any other ship? The answer lies in engineering secrets that most people will never know about. Right now, American carriers are patrolling some of the most dangerous waters on the planet. Beneath their hulls, enemy submarines lurk with weapons specifically designed to break them in two. Above them, storms rage with waves tall enough to swallow buildings, yet these massive warships continue their missions without hesitation. The technology keeping them afloat is nothing short of extraordinary. Introduction. The hull of an aircraft carrier represents over a century of naval engineering evolution. Every plate of steel, every compartment, every inch of design serves a critical purpose. When you look at a carrier from the outside, you see an imposing structure stretching over 1,000 feet long. But the real protection lies hidden beneath the waterline, where layers of defense work together to keep the ship operational, even under the worst possible conditions. From the moment construction begins, these vessels are built to survive direct attacks that would send smaller warships straight to the bottom. The men and women serving aboard these carriers trust their lives to this engineering every single day. They deserve nothing less than the absolute best protection our military can provide. If you support our Navy and respect the engineering that keeps our sailors safe, type PROUD in the comments below. The hull foundation. Let's start with the basics. The hull of a modern supercarrier uses steel plating that ranges from 2 to 8 inches thick depending on location. That might not sound like much when you're talking about a ship over 1,000 feet long, but there's a reason for this specific measurement. Too thin, and the hull becomes vulnerable. Too thick, and the ship becomes too heavy to maintain proper speed and maneuverability. Navy engineers calculated the exact balance needed. The USS Theodore Roosevelt, for example, has hull plating approximately 2.5 inches thick along most of its length. But certain critical areas receive additional reinforcement. The sections around the propulsion systems get extra layers because the constant vibration from 4 massive turbines puts tremendous stress on the surrounding structure. The flight deck receives even more reinforcement since it must support the weight of dozens of aircraft, some weighing over 60,000 pounds each. But thickness alone doesn't make a hull strong. The real secret lies in how the steel is shaped and connected. Modern carrier hulls use a V-shaped design below the waterline. This shape serves multiple purposes. First, it cuts through waves more efficiently, reducing drag and allowing the ship to maintain higher speeds. Second, it helps deflect incoming torpedo impacts away from critical areas. Third, it provides better stability in rough seas by creating a wider base at the keel level. The bottom of the hull features a completely flat design, extending outward from the center. This flat bottom creates what engineers call a stable platform. When massive waves hit the ship, this broad base resists tipping forces. Think of it like comparing a narrow canoe to a wide raft. The raft stays stable because it has more surface area pushing against the water. Carriers use this same principle on a scale most people can barely comprehend. Every single plate of steel in the hull connects to surrounding plates through a process called welding, but these aren't ordinary welds. Naval shipyards use specialized welding techniques that create bonds stronger than the steel itself. Each weld gets inspected multiple times using X-ray technology to ensure there are no weak points. A single bad weld could create a failure point where seawater could flood in during combat damage. Our sailors don't have room for mistakes like that. Watertight compartments. Now here's where carrier design gets really clever. The entire hull is divided into hundreds of separate watertight compartments. These compartments work like the sections in an ice cube tray. If one section floods, the surrounding sections remain sealed and dry. This compartmentalization saved countless ships during World War II and remains just as critical today. Each watertight door aboard a carrier weighs several hundred pounds and seals with multiple locking mechanisms. When the ship goes to general quarters during combat operations, crew members close every single watertight door throughout the vessel. This creates a honeycomb of separate sealed spaces. Even if a torpedo blows a hole in the hull and floods multiple compartments, the carrier stays afloat because the undamaged sections maintain their buoyancy. But there's more to it than just closing doors. Modern carriers include damage control systems that automatically detect flooding. Sensors throughout the hull monitor water levels in every compartment. If water starts rising in any section, alarms sound on the bridge and in Damage Control Central. Trained teams immediately respond to contain the flooding and begin pumping water out. This rapid response capability has saved carriers from sinking on multiple occasions. The compartments themselves serve different purposes. Some contain machinery, others hold fuel. Many are simply empty voids designed to absorb damage. These empty compartments play a crucial role in torpedo defense, which brings us to one of the most important features built into carrier hulls. Speaking of torpedo defense, the method modern torpedoes use to sink ships would shock most people. They don't actually hit the hull at all. Instead, they do something far more destructive. But before we get into that, you need to understand how carriers defend against this threat. Anti-torpedo bulges. Hidden along the sides of carrier hulls, below the waterline, sits a specialized defense system called anti-torpedo bulges. These bulges extend outward from the main hull, creating compartmentalized sponsons that run along a significant portion of the ship's length. The British Navy first developed this technology during World War I, and it's been refined ever since. Here's how bulges work. The outer section consists of void spaces filled with air. Behind that sits another section designed to flood with seawater. Then comes the actual hull of the ship. When a torpedo strikes the outer bulge, the explosion tears through the air-filled compartments first. This initial barrier absorbs much of the blast energy. The explosion then hits the water-filled section, which further dissipates the shock wave and catches explosive fragments. By the time the force reaches the inner hull, it's significantly weakened. During World War I, the British retrofitted several older cruisers with these bulges for shore bombardment missions. One of these ships, HMS Grafton, took a direct torpedo hit in 1917. Apart from some minor damage to the bulge itself, the main hull remained intact. The ship safely returned to port. This success proved the concept worked. Modern carriers incorporate far more sophisticated versions of this technology. The bulges include transverse bulkheads that limit flooding to only the damaged sections. Even if a torpedo ruptures the outer bulge completely, the flooding stops at predetermined boundaries. This prevents a cascade effect where water spreads throughout the entire bulge system. Before we dive deeper into how carriers handle modern torpedoes, please take a second to like this video and subscribe. Over 98% of viewers watch without subscribing. It costs you nothing, but makes a huge difference to us. The modern torpedo threat. Now let's talk about what carriers actually face in modern combat. Today's torpedoes don't work like the ones you see in old war movies. Those vintage torpedoes struck the side of ships, blowing holes in the hull that caused flooding. Effective, but not guaranteed to sink a large warship. Modern torpedoes use a completely different and far more deadly approach. Current generation torpedoes like the Russian Type 53 and Chinese U-10 use magnetic exploders. These weapons detect the metal hull of a ship and detonate while passing underneath the keel instead of hitting the side. This changes everything. When a torpedo explodes beneath a ship, it creates an enormous gas bubble. That bubble expands rapidly, pushing upward with incredible force. The ship literally rises out of the water, lifted by thousands of tons of expanding gas. But ships aren't designed to handle upward pressure. The hull structure provides strength against downward forces from the weight of the ship and equipment. When that same hull gets pushed upward from below, it experiences stress in the opposite direction. The keel bends. Support structures strain. The entire center section of the ship lifts, while the bow and stern remain in the water, creating a sagging effect. For smaller ships like destroyers or frigates, this is absolutely catastrophic. The keel snaps. The ship breaks in two pieces and sinks within minutes. The Australian destroyer escort Torrens demonstrated this during a weapons test. A Mark 48 torpedo with a 650-pound warhead detonated beneath the ship. Video footage shows the Torrens lifted bodily out of the water before breaking apart. The entire process from detonation to complete structural failure took less than 30 seconds. This is what modern submarines can do to surface ships. Aircraft carriers face this same threat. Several nations now field wake-homing torpedoes specifically designed to target large vessels. These weapons track the disturbed water behind a moving ship rather than its acoustic signature. This makes traditional countermeasures like acoustic decoys completely ineffective. The torpedo simply follows the wake straight to the target and detonates beneath the keel. Chinese naval forces recently tested their U-10 torpedo against a decommissioned amphibious assault ship. The video showed the ship breaking apart and sinking rapidly after a single hit. So how do carriers survive what destroys smaller warships? The answer comes down to scale and design. Carrier survivability. An aircraft carrier displaces over 100,000 tons. That's roughly 10 times heavier than a destroyer. When a torpedo explodes beneath a carrier, the gas bubble still forms. The ship still experiences upward lift, but the sheer mass of the carrier makes breaking its keel incredibly difficult. The structural members running the length of the ship are massive steel beams designed to support the weight of the entire vessel. These aren't the relatively thin keel structures found on smaller ships. Additionally, carriers spread their weight over a much longer hull. A Nimitz-class carrier stretches 1,092 feet from bow to stern. When a torpedo creates a lifting force beneath one section, the surrounding hundreds of feet of hull help distribute that force. The ship doesn't break as easily because the stress spreads across a much larger structure. Think of it like trying to break a toothpick versus trying to break a 2x4 board. Both are made of wood, but the larger piece requires exponentially more force to snap. The anti-torpedo bulges we discussed earlier also play a role here. Even though modern torpedoes detonate beneath the keel rather than against the side, the bulges still provide some protection. The water-filled compartments in the bulge system create additional mass along the sides of the ship. This extra weight helps stabilize the carrier and reduces the amount of upward movement when the gas bubble expands. Less movement means less stress on the keel structure. Carriers also maintain careful control over their center of gravity. Ballast systems throughout the ship adjust water levels in designated tanks to keep the ship properly balanced. When fully loaded with aircraft, fuel, and ammunition, the carrier remains stable because these ballast systems compensate for the added weight. This same stability helps the ship resist the forces generated by underwater explosions. But even with all these protections, a direct hit from a modern heavyweight torpedo would cause severe damage to a carrier. Multiple hits could potentially sink one. That's why the Navy developed active defense systems, active torpedo defense. Between 2013 and 2019, the Navy installed an experimental system called Surface Ship Torpedo Defense on 5 Nimitz-class carriers. This system combined two components working together. First, a towed array of sensors called the Torpedo Warning System detected incoming torpedoes. Second, rapid launch tubes, called the Anti-Torpedo Device System, fired miniature counter-torpedoes at the incoming threat. These counter-torpedoes measured only 171 millimeters in diameter and weighed 220 pounds. Despite their small size, they carried enough explosive power to destroy or disable an incoming torpedo before it reached the carrier. In 2013, tests aboard the USS George H.W. Bush successfully intercepted 7 practice torpedoes. The concept seemed promising. However, the system faced serious reliability problems. The sensors struggled to consistently detect and track torpedoes in real-world ocean conditions. The acoustic environment near a carrier is extremely noisy with engine sounds, propeller cavitation, and sonar emissions. This background noise made it difficult for the sensors to pick out the quieter acoustic signature of an approaching torpedo. False alarms occurred frequently. Actual threats sometimes went undetected until too late for the counter-torpedoes to intercept. By 2019, testing reports concluded the system didn't meet operational requirements. The Navy suspended the program and began removing the equipment from carriers during scheduled maintenance periods. All 5 carriers returned to their normal configurations by 2023. This doesn't mean the Navy abandoned the concept entirely. Development continues on improved systems, but currently no operational hard-kill torpedo defense exists on American carriers. Surviving heavy seas. Torpedo threats aren't the only challenge carrier hulls must withstand. These ships regularly operate in weather conditions that would keep smaller vessels in port. Storms in the North Atlantic and Western Pacific generate waves exceeding 60 feet in height. These massive walls of water crash over the flight deck with enough force to tear loose equipment and damage aircraft. The USS Kitty Hawk famously plowed through a severe storm, with waves washing completely across the 1,092-foot flight deck. Video footage shows water hitting the bridge structure over 100 feet above the waterline. The ship pitched and rolled but continued its mission. The hull design that allows carriers to handle these conditions goes back to basic naval architecture principles. Remember that wide, flat bottom we discussed earlier? That design creates enormous resistance to capsizing. The center of buoyancy on a carrier sits higher than the center of gravity. This means as the ship tilts to one side, the buoyant force pushing upward actually increases. The farther the ship rolls, the harder it tries to right itself. Naval engineers call this a self-righting moment. It's the same principle that keeps sailboats from flipping over, but on a scale hundreds of times larger. Carriers also use active stabilization systems. Fins extending from the hull create hydrodynamic forces that counteract rolling motion. When sensors detect the ship beginning to roll, computers adjust these fins to generate opposing forces. This doesn't stop the ship from moving with the waves entirely, but it significantly reduces the severity of rolls and pitches. Crew members and aircraft experience less violent motion, making operations safer and more effective. The hull strength required to handle these conditions is immense. When a 100,000-ton ship rises on a wave, the bow and stern are momentarily unsupported by water. The entire weight of those sections hangs from the center of the ship. Then, as the ship crests the wave, the center section becomes unsupported while the ends are in the water. This creates alternating stress called hogging and sagging. The keel must be strong enough to handle this constant flexing without developing cracks or weak points. Our Navy's carriers handle this stress day after day, year after year, because American shipbuilders know their craft. Damage control, excellence. Even with the best hull design and defensive systems, damage will occur in combat. That's where the human element becomes just as important as the engineering. Every sailor aboard a carrier receives training in damage control. When a torpedo hits, when flooding begins, when fires break out, these highly trained professionals respond immediately. Damage control teams carry specialized equipment for plugging holes, reinforcing weakened bulkheads, and pumping out flooded compartments. They work in conditions most people can't imagine. Waist-deep water, toxic fumes, complete darkness. The ship rolling violently, alarms blaring, and they do their jobs anyway because they know their shipmates depend on them. This is the true strength of an aircraft carrier, not just the steel hull or the advanced technology, but the quality of the people serving. Aboard. The compartmentalized hull design works because trained sailors know how to use it effectively. They know which compartments to seal off, where to establish pumping operations, how to shore up damaged areas to prevent further flooding. During World War II, carriers like USS Yorktown survived multiple bomb and torpedo hits because damage control teams refused to give up. That same spirit continues today in our modern Navy. The hull of a carrier provides the foundation, but the crew provides the will to keep fighting. Together, they make these ships nearly unsinkable. Our sailors deserve recognition for their skill and dedication to their mission. Conclusion. Aircraft carrier hulls represent the pinnacle of naval engineering, multiple layers of defense from the V-shaped bow cutting through waves to the anti-torpedo bulges protecting the sides, watertight compartments that contain flooding, massive structural members that resist breaking even under extreme stress, active stabilization systems that smooth out rough seas, and supporting it all, highly trained sailors ready to respond to any emergency. These ships carry the might of American naval power to every corner of the globe. They protect freedom of navigation. They respond to disasters. They project strength that keeps our nation safe. The next time you see footage of a carrier at sea, remember everything working beneath that flight deck to keep it afloat. Make sure to hit the like button and subscribe for more content about the incredible technology protecting our military. The engineering protecting our sailors deserves respect. So do the men and women who trust their lives to it every single day.